Okay, so we're now going to discuss multivariable integration. First, recall back to the definition of single variable integrals. The integral from a to b f of x dx gave us the area underneath a curve from a to b, and this was equal to the limit as n goes to infinity of n, the sum of n starting from, oh, perhaps I should use, okay, from k starting from 0 of f of xk delta x, where delta x was our fixed width given by the difference between b and a divided by n. Here, what this essentially tells us is that the Riemann summation was used to find the infinite area, or the infinitesimal area underneath each segment, so that more rectangles that we have meant a better approximation, and hence led to a continuous case given by the integral. Now, for multivariable integration, we have the same thing, except across many different parameters. So, to start off, let's suppose we have the same ones from a to b and c to d. F of xy dx dy. Over here, this is equal to the limit as some variable n m goes to infinity for both cases of the sum of n going from k equals 0, and then the sum of m going from, let's say, p equals 0, of f of x k y p delta x delta y. Here in this situation, instead of having just Riemann sums, we have Riemann slices across two different dimensions. And usually we don't use this definition, but this is generally the idea, where instead of using rectangles, we use rectangular prisms, and if we have one more variable, we have 3D spaces. But in general, the format is the same. Okay, so integrating across different parameters, we have to consider a few theorems. One of them is Fubini's theorem. Fubini's theorem states that the integral is interchangeable, so the integration is interchangeable so long as you keep the parameters consistent. So for example, if we have the integral from a to b, the integral from c to d, of f of xy dx dy, this states the following. This is interchangeable to the integral from c to d, the integral from a to b, f of xy dy dx. Now, the only exception to this is that these boundaries have to be constant in order for that to happen. If it happens that the boundaries are based off of a function of another set of variables, like for example, a was dependent on, let's say, a of x, and b was dependent on b of x, then we can't apply Fubini's theorem in this situation. So, but just in general, when we have constant parameters, then Fubini's theorem always can apply. Now we have symmetry. So symmetry in general states geometrically some properties of different shapes. A cube, for example, could represent 3D Cartesian. And as such, 3D Cartesian could help us solve for different problems, such as maybe the flux through something, or in general leads us to a generalization about making an easier calculation. However, sometimes we might use other shapes. A cylinder, for example, is perfect for when we're calculating maybe a magnetic field generated by a current carrying wire. Or we can use a sphere in the case when we're talking about later on, or you might hear about Gaussian surfaces, where we use Gaussian symmetry, or we use symmetry based on Gaussian surfaces to help us find the electric flux of a charge, or a line of charge, or a distribution of charges. So that is what is meant by symmetry. When in multivariable integration, integrating across different parameters helps us understand an easier way to integrate across something. In the next few videos, we'll be talking about how to convert from a 2D Cartesian or a 3D Cartesian into cylindrical or spherical coordinates, as well as polar coordinates. All right. Thank you.